It's a real pleasure to be here. Thank you for the invite, and thank you to Bruno and Martin for setting me up very nicely to talk to you about some topics that are actually quite close to the research end rather than the tutorial end of the spectrum of possible talks that you will see here. I hope that's okay, and I hope it's not too late in the evening to be hitting you with quite a lot of mathematical content. I am an applied mathematician. But I will try and keep the models fairly simple and show you the results with pictures where I can. I'm scheduled for an hour and a half. I have plenty of slides. I won't go over an hour and a half, but I'm prepared to take your questions at any stage and dwell on things that you find interesting rather than racing through lots of slides. So please do stop me at any time with questions. Just before, in case I'm rushing at the end, which I may be, let me thank my collaborators now. There's a big group in University of Limerick. William Lee has just moved to Portsmouth in the UK, and these are postdocs and current and just graduated PhD students of mine. And my international collaborators, the work I'm going to show you today are in particular with this group of people here, our funders of course. And some of the things I'm going to tell you about are referenced here. I'll show you the references again at the end in case there's anything here you find interesting. But of course I'm around, certainly until tomorrow. I'm very happy to talk to you about anything you find interesting. A quick plug for our forthcoming book. This is Mason Porter, my long-standing collaborator in Oxford, and myself have a Springer volume on dynamical systems by network. It is a tutorial that's in proof stage, so that one should be out soon. Okay, so let me dig into a couple of things. First of all, an apology. I am going to talk about static networks, not temporal networks. I gave out to Martin for trying to sell temporal networks ahead of my talk. So these networks will be static, principally because at the mathematical end of looking at processes on networks, there are still plenty of questions that are unanswered or at least open there in terms of the static part of network modeling. So sometimes we take relatively simple network models, but we try and look in detail at what happens on those networks. So forgive me if my networks are static. Most of the time I will talk about configuration model networks. Martin briefly introduced those. I'll describe to you again the construction of those. So I'm not, in general here, at least today, going to talk about things like correlations, high-degree nodes connected preferentially to other high-degree nodes or to low-degree nodes, or clustering the existence of triangles, or perhaps at a mesoscopic level of communities of nodes, or more complicated structures like multi-layer, or as I said, dynamical or temporal networks. Let me stick mostly with configuration model, but several things that I will mention can be generalized into these areas, and again, I'm happy to talk about those later if you wish. Okay, so let's, again, I wasn't sure how much of an introduction you've had. I think you've had a pretty good introduction to models of networks, but let's talk about end nodes or end vertices. I am all the time going to be thinking about the large N limit. That is important mostly to get analytical results of the type that we want. The most important quantity for me is the degree distribution. Again, pk is the probability that a randomly chosen node is degree k. We've seen that plenty of times. I will use the mean degree. I tend to use the letter Z for the mean degree, so just to warn you of that, that's the mean degree of the network, how many edges per node on average. And as I said, I'm going to work into configuration model ensemble. So if you think in a mathematical sense, the configuration model ensemble is an ensemble of possible graphs, for which we give a degree sequence or a probability. And just to give you a very quick idea of how you might set that up, you take n nodes, and n, as I said, is going to be a large number, and you have an assigned probability that a node should have a given degree k. So you take your n nodes, here are 6 of them, but there should be very many of them, and you assign stubs or half edges to the nodes. Depending on what P1 is, I'll have a certain number of nodes, we should have 1 stub. Depending on what P2 is, I have a certain number of stubs that have certain number of nodes that should have 2 stubs, and so on. So by construction, I'm making sure that my network has the right degree distribution. And then, having set all these nodes out like this, we pick pairs of stubs at random, as I'm doing here, and join them to form an edge. So by doing this, and provided that I initially had an even number of stubs in the first place, I generate a realization from this ensemble. So one possible network which has this degree distribution. And as you can see, this construction pretty much randomizes everything else. So by construction, it's more uncorrelated. There are no special degree correlations. There are rarely, only do you get triangles, clustering and so on. Okay, so that's the configuration model ensemble. And that's again where most of our analytical work will be done. Some of the results do generalize beyond that. Okay, That's on the network side. On the stochastic processes side, or the dynamical processes side, what are we talking about? So we're looking at stochastic processes, and the stochastic part is particularly important here. So you'll see examples. You have seen some examples already. So I won't talk much about percolation, but percolation is really the underlying object that sits under a lot of these types of contagions. Biological contagions, Bruno gave a very nice introduction to SI, susceptible and infected dynamics, and SIS and SIOR. I'll talk a little bit about more some of those in that sense. Social contagions, I'll mention also. So Martin specifically mentioned threshold model. So what is a threshold model? A threshold model is on a social network. So again, nodes are people, the links are social contacts, it's static. And the idea here is that we're talking about the adoption of perhaps a new product, and not a simple product, but perhaps something expensive like a phone. Okay, so a new phone. If one of my friends gets a new phone, it's not immediately the case that I will rush out and get a new phone. But it might be the case that if 2 or 3 of my friends have gotten a new phone, then I'll be more inclined and more likely to do so. So the threshold models of social contagion like that, or of adoption, require that not just that a single person in your neighborhood has adopted or become infected. I'll use infected in the general sense, but that you need more than one. Okay, so more than one infection is necessary. So in contrast, as you probably noticed, to the biological contagions we've seen so far, all the biological contagions so far, if one neighbor is infected, there's either definitely or at least some probability that any one of their neighbors can become infected. That's not necessarily the case for a threshold model, which is only one, by the way, of a whole list of different types of social contagion models. But a threshold model explicitly says I have to have more than one person become infected for me to become infected, and that changes the types of dynamics there. A related model is a whole variety of models called voter models. I'll talk about those in some detail. They are really copying models, so where nodes have one of 2 possible states. The model here is typically of a 2-party system, so if you think Democrat and Republican, and people express an opinion, so it's an opinion dynamics model, and people can change opinion based on copying, usually at random, one of the opinions of their neighbors. Okay, and again, there are varieties of that, but I don't think we've mentioned that one yet today. I'll talk a little bit more about that example later on as well. Let me jump here. Do we do things in discrete time, or do things happen in continuous time? That's an important question from the mathematical point of view. Usually when we simulate things on the computer, and we do it as well to look at our theories, we do things in discrete time. Right? That's just by the nature of doing computations. However, there's an argument that a lot of things happen in continuous time. And when we use this to approximate this, we have to sometimes be quite careful about doing it. In particular, when we update our models, when we look at the nodes in the network and they're possibly changing state, do they all possibly change state at the same time? Okay, that's a very, very restrictive type of discrete time updating, and that's called synchronous updating usually. Or do we allow asynchronous updating, so nodes perhaps change their state or consider the possibility of changing their state at random times? So that's something we'll come back to. Most of what I'm going to tell you today sits in this asynchronous or continuous time space. And something I'll get to perhaps towards the end is about memory effects. So, and this is somewhat related to the temporal networks ideas that Martin was talking about before. Most of the standard models that we've talked about are Markovian. As Bruno mentioned, Markovian means essentially memoryless. So we're given the state of the system, the network, and the states of all the nodes, and that in itself is enough information for us to figure out what happens next. This is a hazy word, but essentially if there's something in the system that means it has memory of the past, or that the past influences, not just a snapshot of where the system is at the current moment in time, it's a type of, at least is more involved than a simple Markovian process. And I'll show you towards the end some examples of where that's important. And this is, I guess, increasingly important, where we have data on how people behave when they do things like spread social contagions, and memory is an important aspect of that. Okay, so I've kind of split the talk into 2 parts. I may or may not get into too much detail on either, depending how we get on. The first one I've called supercritical dynamics. So this echoes or expands on some of Bruno's work this morning, where he was introducing you to the notion of using differential equations to model contagions. Okay, so if you remember, he had the homogeneously mixed SI model at the start, and then he introduced the mean field, the heterogeneous mean field, where things were gathered into degree blocks. We've done some work in the past on looking carefully at that mean field approximation and saying, okay, that is an approximation. It's not always accurate. under what circumstances can it be more accurate? And in fact, the way I'm going to introduce it to you is throwing you in the deep end. I'm going to show you a high accuracy approximation, and then we'll work our way backwards to say where the mean field approximation comes from, that high accuracy approximation, and try and understand more about when mean field is an accurate approximation, when it's not. Supercritical means that using differential equations is an appropriate thing to do. When we use the differential equations, we say we can describe the fraction of nodes who are, let's say, infected in the disease spread model in a big network, and I can use a single number at each moment in time to describe that. Okay? I'm not thinking about the distribution of possible nodes who are infected. I'm thinking about a single number that describes the state of the system at that moment in time. Bruno showed you some nice examples of stochastic trajectories. Okay, so if you simulate it, you find that not every historical simulation is exactly the same. And the assumption here is that the mean, the average of those describes it well. That is true in most of the cases that people look at up here, but what I want to get at down here is cases where that's not true. So if you have a disease, for instance, and it spreads to only a few people, maybe it spreads to a few dozen people, maybe it spreads to a few hundred people, or maybe you're on Twitter, which has 300 million users, and something spreads to 4,000 people. Okay. Is that a substantial fraction of the size of the network or not? And if it's not, if we repeated the exact same experiment tomorrow with the exact same piece of information, it's entirely possible that 4,000 people it spread to might instead be 40 people. Okay? So in those cases, you get finite size outbreaks, and the outbreaks are typically not well described by their mean. Okay, so up here, supercritical dynamics, the outbreaks typically are well described by their mean. And to get to this case, you need to have either a large enough seed or a well enough connected network. Here, if you're close to the critical point of dynamics, you may not get that. So I'm going to try and show you a little bit about this as well. But let's start up here in part one, and we'll see how far we get. Again, please do stop me with questions. So the goal here is to think about this single number, the fraction of infected people in a network. And I want to predict that. Okay? Mean field approximation is a good thing to think about. What do I know? I'm going to assume that I know the local interactions. So I know a disease spread model, or I know a threshold model, or I know the voter model. I know something about how agents interact with each other on a local basis. And I know something about the network structure. Again, typically I'll at least start with the configuration model and say I know the degree distribution. So those two pieces of information, what do they allow me to say about the macro scale diffusion? So what would be observed by, I don't know, someone who's CDC, who's monitoring the spread of a disease through a population on a global level. And again, this is an old problem, it's not a new problem. If I say the fraction of infected nodes, and again I'm going to use infected here just to mean one of two possible states. You'll see some examples in a few minutes. That fraction rho of t can be approximated in various different ways. We can simulate it numerically and get, if you like, the ground truth for it. The mean field methods that Bruno mentioned to you are one approximation, and they are accurate in very many circumstances, but not all. People in epidemiology in particular have looked at what's called a pair approximation, so looking not just at the mean field, but at two ends of an edge and asking how that affects the spread. I'll show you some examples in a second. And of course, the master equations that Bruno discussed this morning are really capturing the whole system, and these two objects are somehow simplified versions of this how do we get the disease. Okay, and when I'm talking about small intervals of time, that's an accurate way of thinking about it. So you see these rates occurring a lot, so I'll try and express those for you again in a few minutes. This is a well-studied problem. Pastor Satoris and Vespignani's, I guess, seminal paper in 2001 looked at mean field methods for SIS and derived the result of the epidemic threshold vanishing in scale-free parallel networks. It's been examined more closely under pair approximations and in recent years using approximate master equations approaches. And you'll see why. I'll show you some examples where mean field doesn't do a very good job of predicting SIS disease spread. The voter model, which we haven't talked about before. So I mentioned it to you already. We'll let each node be a person and have one of two possible opinions. Again, just to keep the notation simple, I'm going to call the opinions infected and susceptible, but these shouldn't be thought of in any disease spread sense. They're just two possible peoples that the node may have. At each time step, and here we think in discrete time, where usually the discrete time step that's used in the voter model is 1 over the number of nodes. Okay? We choose one of the nodes at random, and that means it's updated, so we choose it at random, and how it updates is it picks one of its neighbors at random and it copies the opinion of that neighbor. So if I'm surrounded by people who have a different opinion than me and the node that's updating, I will have to adopt that opinion. But otherwise, the overall opinions across the network can vary quite a lot, can fluctuate quite a lot. particularly if we start them with roughly equal levels of popularity. So the mean field for voter model was, I think, first studied by Sood and Sid Redner in 2005, and various pair approximation schemes have been tried for voter model as well. It's an interesting case to look at. So those are two examples, and what I want to do is try and put it in a general framework. Okay, we're going to give you a whole lot more examples in a couple of minutes with a table. So to put that table in context, let's think of a general sense where we have n nodes, and each of the nodes is in one of these two possible states. And again, arbitrarily, I'll call one state susceptible, the other one infected. To get us started, we'll have some randomly chosen fraction of nodes which are initially in one of the states, the infected state. In a small time step dt, we'll update some small fraction of nodes. Okay, so that's asynchronous updating. An updating node that is susceptible will become infected with a probability. So there's a rate involved here, and there's if I'm in a time step dt, it's multiplied by this time step to give me an overall probability. And I want the rate f here is for infection. Okay, so think f is for infection, and I'm going to allow it to depend on two things. One is on the degree of the node, okay, and the other one, m, is the number of neighbors that are already in the infected state. Okay, so the dynamics, and I'm going to show you that a lot of sort of well-known examples of stochastic dynamics can be cast in this framework. Dynamics are that the node state change or transition probabilities depend on the degree of the node and the number of its neighbors who are in one of the states. Okay? Yeah. So they're all like that. There's white is susceptible, black is infected, and the f km is the infection probability for a k degree node who's susceptible, who has n infected neighbors. And vice versa. So in general, we'll allow, if you like, recovery. So I'll denote that or the rate, and that's the rate that a node switches from black to white, if you like, in these pictures, given that it has, again, n infected neighbors in its degrees k. Okay. So for instance, go back to the voter model that we talked about. Okay. I explained to you how the voter model works. If you think about it in the sense of the rates that we have here, so suppose I'm chosen as the node who's updated, okay, in time step dt. What's my probability of becoming infected? So if I'm susceptible, what's my probability of becoming infected? Well, I'm going to pick one of my neighbors at random. Okay. I have m infected neighbors, and I have k neighbors altogether. Okay, so what's my probability of becoming infected? Well, it's just the probability m over k that I've picked one of those infected guys and copied him. If on the other hand I'm in the black state or the infected state, what's the probability I'll move to the white state? Well, again, it's the probability that I'll choose one of the k minus m of my neighbors who are in the white state out of the k possibilities that I have there. Okay, so that's one example of a dynamic that can be written like that. Back to the SIS disease spread model. If I think about that, here I am susceptible. What's my probability to become infected? Well, I have m infected neighbors. Each of them can infect me at a rate lambda. Okay, you can be a little bit more careful about that. Bruno showed you this kind of calculation this morning. This is the probability that one of those neighbors does not infect me. This is the probability that all m of them do not affect me, and this is the probability that I become infected, and 1 minus that. And if my time step is small, dt is small, that's lambda m dt. So my rate is the lambda m bit multiplied to dt here, that's my f km. Whereas recovery is a constant rate, it doesn't depend on how many of my neighbors are in any state, so that's just something that can happen once I'm in the infected state. So here again are the f and the k functions for SIS. Right, so this table from the paper gives a list of a bunch of those kinds of functions. Did I kill my microphone? Sorry. The infection rates and the recovery rates for instance, SIS disease spread, SI disease spread, which is just SIS without the recovery. Okay, recovery set to 0. These are adoption models. The vast model of adoption in marketing it's essentially an SIS-like model, but it's used by people in marketing. The voter model, I've already shown you the F and the K for that. There are, as I told you, variations of voter models. The majority vote model we didn't mention. Here's a kind of a picture of it. So I'm showing you the F, the infection rate, and K, the recovery rate, or in red, as a function of the number of my neighbors who are infected. Okay, so I have K neighbors altogether. This is the number of them that are infected. So majority vote, in the simplest possible case, this Q parameter is 0, and I just go with the majority of my neighbors. Okay, so if more than half of my neighbors are infected, when I'm updating, I'll become infected too. If less than half of my neighbors are infected, when I'm updating, I'll become susceptible. That's the red here. And the Q is kind of a noise parameter, so sometimes just because more than half my neighbors are infected doesn't mean I'll necessarily do it, so this is at 1 minus Q, and so the probabilities are not definite in those cases. Up here is a picture of the SIS case that we already discussed. The recovery rate, as I said, is constant. It doesn't depend on how many of my neighbours are infected, whereas the infection rate does. It's linear in the number of my neighbours are infected. So that's just a way of sketching those. And here are two more examples. Those of you who are physicists will recognise the Ising model for spins. So for spin up and spin down, those are two possible states that each node in the network can have. And if you're thinking about spin up and spin down on a network, there are ways that those nodes can influence each other through their neighborhood interaction. So the Glauber dynamics for the Ising model, or metropolis dynamics for the Ising model. If you think of spin up as infected, spin down as susceptible, it falls precisely into this type of category. The infection rates and recovery rates are sort of logistic functions like this, but depending on the temperature of it, the steepness of this curve can go up like that and go down like that. Again, you tend to go with the majority, but perhaps not definitely. There's a temperature in the Ising model that tells you how likely you are to go with the majority. And finally in this list, the threshold models that we discussed at the start, or I mentioned to you at the start. So these are what I call monotone models. So there's only one-way dynamics. You can't give back the iPhone after you bought it. So if we're talking about adoption of an iPhone, if infection here is the spreading of iPhone through a population, but you can't give it back, so no recovery. And typically there's a threshold here, so I will buy an iPhone if M, the number of my friends who've already bought an iPhone, is above a certain number, and that number in general might depend on my degree. So often the number is thought to be proportional to the degree, but there are other varieties of threshold models out there. The important point is it's not a dependence that's just at M equal to 1. So in my picture here, the recovery rate is 0, the reds, but the blues, you can just see that there's 0 for 1, 2, 3 of my neighbours. So even if 3 of my neighbours have adopted, my probability of adoption is still 0, but once it hits 4, it goes up to 1. So if I'm the chosen node to update then, and more than 4 of my neighbours have bought the iPhone, I have to go buy the iPhone. Okay, so those kind of threshold models are Granovetter, Watts type of models. And they have, as I said, interesting dynamics that's not quite the same as biological equations. Okay, so and why is any of this interesting, and why do we have to go beyond mean field? This is trying to motivate that. So sticking with the threshold model, and sticking with the simplest possible network that I could come up with, this is what we call a 3 regular random graph. So every node is degree 3, okay? Very, very simplified situation. So this is a delta function of 3. And I'm going to set the threshold here to be 2/3. So what this means in practice is that everyone has 3 neighbours, okay? And if 2 or 3 of their neighbours have the iPhone, they go out and buy the iPhone. If 0 or 1 of their neighbours have the iPhone, they won't, okay? And no giving back the iPhone, all right? So how does adoption spread in that community? If I'm Apple and I, for instance, want to seed the network with some free iPhones, what fraction of the population should I seed the population with to get an overall? So this is time. This is the fraction of people who are infected, bought the iPhone. Okay, so this starts with a fairly big fraction of 40%. The black is from numerical simulations, so large-scale simulations, doing like what Bruno was showing you, lots of trajectories, taking the average, and the average is doing this, and it's stopping here before it gets to one that's bad news for Apple's world domination, and it's contrary to what the mean field theory for this situation is telling you, which tells you that it would pretty rapidly go to 1. Okay, so that's interesting. That's a challenge. We did a lot of work on threshold models a number of years back. This was one of the examples that bothered us a lot. There are ways of calculating this, and we also want to deal with the case where you could give back the iPhone, essentially, or where you're dealing with threshold models which work both ways, and I'll show you some examples of that in a minute. Okay, so mean field. Let me first talk about mean field. So what is mean field? I guess Bruno described it really well this morning when he said, if I'm the node who's updating and I'm doing a mean field approximation, what I pretend is that all my neighbours, who are, let's say, 4 from this node here, all those 4 neighbours, I just pretend that those are somehow sampled from the overall population. That the overall fraction of infected nodes in the population, that's the probability that each of my 4 neighbours is infected. And I use that in my analytical approximation to figure out how the node will update. Pair approximation is a little bit more involved. So what mean field is doing is it's saying, okay, I'm pretending the states of each of these 4 nodes is taken from the overall population, but I'm ignoring the fact that they're all connected to me. Okay, so suppose I'm susceptible. That does affect the states of my 4 neighbours. Okay, there are not degree-to-degree correlations, there are dynamical correlations here. So that if you know the state of one node of the network, you have some information and you know that this is a spreading process, then that immediately tells you something about some of his neighbours. Okay, not for sure, but there are correlations in there. Pair approximation tries to use that information or approximate it a little bit better. So in cartoon form, what a pair approximation does is it looks not at the 4 of my neighbours individually, but at the fact that there are 4 links, and those links are linking me to them. So if I know my state, I know something about one end of the link, and that allows me to say something a little bit more accurately about what perhaps is happening at the other end of the link. So the states of these 4 guys, I'm not just pretending they're fully mixed in the network, they're from the network, but they're connected to me who is susceptible, and that gives me some extra piece of information. Okay, it's a more complicated approximation to be more accurate. And the master equation, which I'll tell you about in a minute, is just taking the whole neighbourhood and trying to describe, if I know my state, trying to describe what the probabilities of my neighbours being in each of the other possible states might be. Okay, so that's a kind of cartoon picture that I hope will clarify what I'm doing here. Okay, so let's look at the mass. I'm going to throw you in the deep end. I'm going to show you the hard bit first, and then we'll work our way backwards to the mean field approximation, the easier approximations, and try and understand what we're losing as we go back. So bear with me a second, this is perhaps the harder, more complicated part. To make it easy, I'm just going to start with, again, z-regular graph. So let's assume everyone has the same number of neighbours. And I'm going to focus on me. Okay, this is on the ego node here in the middle. So here's me. And in all the cases on the top, I'm saying, let's look at the ego node and say, how many of these neighbours are infected? So here, M is actually 1 in this case, is 1 infected, here are 2 infected, here there are 0 infected. And on the bottom, it's the same kind of situation where the ego node is in the infected state rather than susceptible state. So we call these the SM classes, and these the IM classes, right, for obvious reasons. We can break those down to the fraction of nodes who are susceptible and have M infected neighbours. So basically every node in the network must live in one of these compartments. So we're back to Bruno's idea of boxes and moving things from one box to another box. That's all we're doing here. It's sometimes called a compartmental model. But every node can be put into one of these boxes at any moment in time, and we want to know how do things move around in this dynamics in these boxes in as accurate a way as possible. We know something about the initial state. So a fraction, rho 0 of the nodes are initially infected. So if I want to be a susceptible node with M infected neighbours, I'm susceptible with this probability, right? 1 minus the infection probability. And I have M infected neighbours, well, this is a binomial distribution. So if I have Z neighbours, remember everyone has Z neighbours here, then the probability that M of them are infected is just given by a binomial distribution or Bernoulli distribution on Zn. Don't worry about it too much. It's just an easy way of me figuring out how many of my neighbours have to be infected if they're all assigned randomly at the start. Okay, so what can we do? Well, one thing you can immediately do for this setup is say, if I know the number of nodes, the fraction of nodes that are in any one of these states, then the number of nodes in that state is n times Sm. And if I want, for instance, to count the number of SI edges, once I get into things like pair approximations, I want to know what's happening at both ends of an edge. So the number of SI edges, one way of counting it is to say, I get an SI edge if I'm in an SM class myself. And if I'm in the SM class, I have M edges from me to an infected node, right? Because M of my neighbours are infected, so each one of those gives me an SI edge. So I can get that by just counting up the M times SMs and summing over the possible M's, and that gives me immediately the number of SI edges in the network. You can do similar things to get all the other edges. Once you have that, you can think about the transitions that can occur. So let me just think about the threshold model example I showed you earlier. And again, let's not allow recovery for starters off. So how does the size of this SM class change? Well, it changes in a couple of possible ways. Nodes, if you like, leave this box and go to this box if the ego node in the middle becomes infected. Right? So if I'm living up here and I become infected, I change my state, then I move down to here. And what rate does that happen at? Well, that happens at rate f, and f depends on m, the number of neighbours who are infected. Okay? I've dropped off the k here because everyone has the same k, so I don't need to hold that here. So in terms of the size of the number of nodes in that fraction, it's decreased by this transition here. It's also decreased by nodes. The ego node stays susceptible in this transition, but one of his neighbours, one extra neighbour has become infected, right? It'll go from here to here. So that happens. What's the probability of that happening? Well, it happens by one of these edges, these susceptible edges, this one in fact, becoming a susceptible infected edge. Okay, so I need basically this edge to change that type. So if we know the rate at which edges change, or links change their type, like this, and I count the number of susceptible links that I have here, okay, I have Z minus M of them, I have M infected, so I have Z minus M susceptible neighbours, and I'm susceptible. So that counts the number of such edges, and this is the rate they change at, so that's the nodes that move in this direction. And there's only one other transition that can happen, and that's nodes coming into this state from this one here. And again, that happens by one edge, this one in this case, going from susceptible to susceptible infected. Okay, so again, you can easily figure out what that is. And that's it. That's all the possible transitions that can occur. So if I'm prepared to have a box or compartment for each of the classes of nodes, the SM nodes, and M goes from 0 up to Z. Z is only 3 in this case, so that's 4 equations, 4 differential equations. That's not so many in a modern day solver. And here's the approximate part. Everything I've told you so far is exact if you can calculate these things exactly. But there is an approximation in figuring out what this rate of edges changing rates is. Basically, I'm approximating by saying I want to know what's the rate at which edges like this become edges like this. Okay? And I do know what happens here. If I'm looking at the ego node, I know the probability that he becomes infected like this. So if I use, and now I'm taking an approximation over the whole network, and I can figure out that rate, beta S, in terms of quantities that I'm working with here, dynamical quantities in my system, the SMs, the FM, which is it's a rule of my system, and these are just sums. So basically, if I have the SMs and I track the SMs for this number of SM classes, and I use this in here, I get a nonlinear differential equation system which models the dynamics pretty well. And then once I have that, I have my initial condition for all my classes, I can figure out what the infected fraction is, and I told you that was the thing that was genuinely interested. I can also figure out other things, but this is the one that we were interested in. So the fraction of infected nodes is 1 minus the total fraction of susceptible nodes, obviously. Okay? So if you do all that, and this is the picture I showed you a little while ago where we had the numerical simulations which did poorly compared to, or for which mean field did poorly, indeed doing a bit more work, quite a bit more work in fact. We're solving 4 differential equations compared to 1. We get very good answers. Okay, so that's encouraging at least. More usefully though, it also allows us to extend this, right? So I showed you everything just for infection only, and I won't go through the details, but I think you'll easily believe that we can now allow recovery as well. So recovery holds like this, and if you allow recovery, this node can recover back to here, so you get transitions this way, and you get transitions these ways. So you have a full set that looks more like this, okay, and now you have to track not just all the susceptible states, but all the infected states as well. But all the arguments go through. So again, you get a closed system of differential equations, though you know dynamical systems. This is genuinely a nonlinear dynamical system of an order that depends on how many complicated compartments you have to keep hold of, keep track of. And if you allow recovery, for instance, you could consider a situation where you can give back the iPhone. It's probably not a great example to be using at this stage, but where nodes become infected if more than 2 or more of their neighbors are infected, and they recover or they give back the iPhone if less than 2 of their neighbors are infected. So in that case, if you start with 40% infected, it turns out that you would go down. The red again is the approximate master equations, the black is the numerical simulations, and the green, just for contrast, is the mean field theory. So there's quite a difference there. Again, on that simple case. It is a simple case, so again, you can generalize it a little bit more by having a general degree distribution. So I showed you everything for Z regular, just to make it easy to understand. If we now extend the classes such that there's a K and an M, and now you're getting into big systems of differential equations, but in principle, everything goes through. So you get these classes of differential equations with the rates which depend on your system, and you get, again, some good results. So for instance, and this kind of thing people have done before for SIS. All I did here was add in some, I guess, observations on how general this kind of method can be for different types of stochastic processes. So you remember SIS, as I said, this is done by a group in Canada, Marceau et al. Dubé's group in Canada, and I think independently also in Canada, this group. Black here again is numerical simulations. So I'm looking on my simple graph, 3 regular graph with this infection rate and this recovery rate. This is close to the epidemic threshold, so we're getting to situations where mean field can be not quite as accurate, and that's seen here. So there's the original mean field theory, the green line. Again, the fraction of infected nodes in this, again, very simple network, static and very simple even topology. Pair approximation does much better, and the approximate master equations do really quite well in this situation. As you get closer and closer to the threshold where this black line gets closer and closer to 0, then even the AME does not become quite so accurate, but it's better than the other two. I don't know if I have time to show you a demo, but I guess the major drawback of this whole scheme, insofar as I've shown you so far, is just the sheer number of differential equations that arise in it. They're messy to write down, and you can imagine they're a nightmare to code. So we've done that. We've done all the hard work of coding that and made it available. So the idea is that all you should have to describe is the degree distribution of your network. So the configuration model network, you tell me what the degree distribution is, and you tell us the rules for the transition rates from going from susceptible to infected and vice versa. So if you code both of these, you code this, then the rest of it is just differential equation solving, and there's plenty of code available for doing it. So let me very quickly show you. Free to download this and run it. So for instance, this code here says, there's some graphs that we've hard coded into it. So a Poisson random graph, an Erdős graph with mean degree 7 and cutoff degree 25. I want to do Ising dynamics or Glauber dynamics with these parameters. This is the initial seed fraction, this is the end time, and this is just telling you what to show me in the end. So you plug that in, you get a bunch of differential equations which are solved, both coded up and solved automatically. And depending on the output you asked for, you get the fraction of nodes in the infected state. So to start from that 0.51, we set as the initial condition, and then the mean field versus the AME and the pair approximation. And you can get other statistics as well, like the fraction of SI edges, the fraction of edges that connect S to I's. One other example there to show you. This is a Z regular graph, and if you want to put in your own F function, so it's a Z regular graph, you can have number of infected nodes going from 0 to 5. So if you just say what's the this is a threshold model now, so the probability is 0 if 0 or 1 of the nodes are infected, but if 2, 3 or 4 or 5 are infected, the probability is 1. So this is the iPhone type example with no recovery, all zeros. And again, plug it in and run it, it's quite fast, as long as you don't have too many degree classes in the model. Okay, and again, in this particular example of threshold adoption, the mean field theory would tell you that the whole population will adopt the iPhone, whereas the AMEs, which match the numerical simulations very well, will tell you that's not going to happen in this case. Okay, so again, we're quite near a critical threshold in the model. Okay. So I've shown you a little bit about that. I did tell you at the start that I would throw you in the deep end in order to tell you something about these simpler things. So let me briefly finish this section by trying to explain how you do that. This is the full complicated set of equations where we track each compartment. If I do what's a pair approximation ansatz, the pair approximation basically says that if I'm a susceptible node, then all my infected neighbors are basically similar to me. Okay, so the probability of me connecting to an infected neighbor is given by this single number pt, and the probability if I'm infected of connecting to an infected neighbor is given by another number qt, and there's the fraction that nodes of degree k are infected, the probability that nodes of degree k are infected, that's say, like in the heterogeneous mean field. So if you say, all right, this is an ansatz, I'm going to pretend that the number of neighbors who are infected is binomially distributed, that's this b here, then I get standard pair approximation equations. So if you plug those into this big system and you work out what the equations look like, you get this much smaller system, it turns out, of yellow equations. I know it looks complicated, but it's much easier to implement. And if you further approximate it by saying, okay, whether I'm connected to an infected person doesn't depend on whether I'm infected or not, so there's a single number omega here, then you get a mean field approximation. So if you take, for example, the infection recovery rates for SIS and you plug those into those equations, you get standard pair approximations for SIS, and you recover the classic mean field theory of Pastor-Stewart and Vespignani. So in that sense, mean field theory is here as a twofold simplification from a more complicated model up here. Similarly, in a Volter model, if you take the pair approximation equations and the mean field equations that we derive generally and plug in these rates, you get one of the standard pair approximations for Volter model and the standard mean field theory for Volter model. So you can see how the simpler theories emerge from the more complicated, in fact, often unwieldy theory. Finally, on this bit, what do we learn? So one of the things that we learn from these big systems equations is that we get some insights into when pair approximation is accurate. So there's a great deal in the papers about this, but let me give you the overview of it. When is it the case that solving this big system of equations, these approximate master equations, and the relatively smaller systems of equations that are called pair approximations, when is it that it's not worth doing the extra work? Okay? Or to put it another way, these are often easier to derive, so when should we work with the simpler equations? So we can show that you get identical results for the complicated system and the less complicated system if and only if your infection rates are of a special type. In fact, they have to be linear in the number of infected neighbors. That's just a result that falls out of the mathematics of the right-hand sides of all those equations. So for instance, SI disease spread, which is a classic case, which is exactly of this form here, A is 0 and B is a constant, then you get a formula like this, and indeed if you check it, the AME, the red, and the pair approximation blue are exactly the same at every moment in time, but there, and this is the fraction of edges that link susceptible and infected nodes, they're identical in both cases there. So that's, I think, a useful piece of information. The B here doesn't have to be positive. You could have a case where having more of your neighbors infected makes you less likely to be infected. Okay, so B is a negative number here, that's what I've drawn here. The infection rate decays with them. Right? So that's, people have talked a little bit about these indie models. So the more that my friends like something, the less likely I am to adopt it. Yeah. So that's what's going on here. The more of my friends like something, the less likely I am to adopt it. So hipster or indie models. But even there, the pair approximation and the AME, because it fulfills these what are just mathematical requirements for the things to be identical, it turns out to be enough. So that's, I think, also a little bit interesting. But it doesn't quite hold once you go looking at infected, susceptible, infected triplets. Okay, but that's perhaps a little bit more too complicated for here. Okay, one more thing that's interesting here is that what I asked about in the previous case is I wanted the things to be identical at every moment in time. Okay. Now, often we're not interested in every moment in time. We just want to know what happens in the long run. Okay, in the equilibrium situation. So in the equilibrium situation, t goes to infinity. Then again, the pair approximation and the AME solutions are identical if the mathematics tell us that the rates, the infection rate, recovery rate have to have this rather strange relationship between them for some constants b, which depends on k, and some a, which is independent of k and m. And it turns out that Ising spin model dynamics exactly fulfill this requirement. And of most of the models I've shown you, that's the only one that does it. So just to show you that picture, you can see that the red and the blue are not identical at all times, but they are identical at the end time for both the fraction of nodes infected and the fraction of SI links. And if your system is like an Ising spin model and also has an up-down symmetry in it, that allows you to find the critical point. Again, those of you who are students of dynamical systems would have heard of pitchfork bifurcations. So a pitchfork bifurcation occurs at a critical value of this parameter A, and in the Ising model, that's the temperature. So this is a way of getting at the critical temperature for the Ising model on a configuration model network. Again, that's been done before in very different ways, but this is approaching it with a dynamical systems approach, and it generalizes it somewhat to other kinds of stochastic dynamics that obey this criterion here. And that's not everything. So, for instance, the majority vote model does not obey this criterion, and just to demonstrate that to you, there's the AME, which matches the numerics well, but it's not the same as the pair approximation in its equilibrium. So it's a non-trivial relationship to ask, or non-trivial question to ask whether those two things are different. And again, it's related to microscopic reversibility. It comes back to detailed balance, from Bruno's talk this morning, between those systems. So it's you need to be able to go back and forth with equal possibility along these ways. So it's a rather complicated thing that's still under investigation. So it's a good place for me to stop this section, just conclude and remind you what I talked about. It was really focusing on this approximate master equation approach. I suppose maybe the main take-home message is that there are lots of stochastic dynamics that you can define in this way, as long as they're Markovian and depend only on the number of your neighbors or one of the states. It does things like give us the pair approximation and field equations immediately, and also tells us something about when those are accurate. And again, please do download and play with those equations if you're anyway interested to do so. Okay, so that's the end of part one. Do you want to give me any questions on that, or should I fire ahead? No? Okay. Let's drive on and see how we get on with part two. Again, to review here is that I'm getting differential equations here. So things they were of the order of the system size, so I was talking about fractions of nodes that are in given states. Here, there's going to be relatively few of the nodes in states, so the outbreaks are small compared to the network size. That's important really when we go look at applications. So towards the end of this, I'll show you some data from spreading on Twitter. And outbreaks can be of very, very different sizes, so there's distributions of them. So in particular, what I want to do is describe the distribution of outbreak sizes. If you think of disease, I'm talking about the outbreak sizes, and how this depends on the network structure. And I'm going to be really thinking about social effects here, or Twitter meme spreading, viral things on Twitter, how that depends on how people interact in memory, in time. This is not our work, but it's a very nice motivation, I think, empirical work on Twitter. So both these cases, people took very, very big data sets from Twitter, scraped them, and the game was to figure out how popular things become. Okay, so what they, in both these cases, tracked are actually URLs. So URLs on Twitter, they tend to spread without too much modification or too much mistakes. So basically, big data set, you pick out the distinct URLs in that data set. So for every distinct URL, you trace back to when it first appeared in the data set, and then you say, okay, now track that forward in time and see in my data set how many times is that URL used from when it first appeared to the end of my observation time. Okay. However many times it was used, that means tweeted or retweeted by someone, that's its size, that's its popularity. So all this is really about popularity models or cascade sizes. So the story is that most things appear in the data set and they're never retweeted. Okay, so most things here have a size of 1 because they appeared once in the data set and that was it. Nothing happened afterwards in time. However, and these are log scales, so this is a big gap really, right? So this is perhaps 80-90% of all the URLs. And you can't see the dot variable there, but it's there on that one. So again, an order of magnitude down to things that were at least retweeted once, which is what appears here, or twice, or 3 or 4 times, and this is again a log scale. So sometimes, rarely, but sometimes things get retweeted a lot, okay, and they go viral. I don't want to claim these are parallels. Again, like Bruno and Martin, I'm being careful on that, but I am drawing here lines that corresponded to actual parallels, and this would be the parallel if we had a parallel distribution which fell off as exponent 1.5, and this is what the parallel with exponent 2 would look like. So that's size to the power of minus tau. It would be these lines on log scales, and you can see in both cases that whatever's going on in these fat tail distributions are falling somewhere between the 1.5 and 2 exponent, which is quite a steep, quite a fat tail in a distribution. Again, these don't go off forever, but if they did go off forever with an exponent 1.5, not only would you not have a variance for this distribution, not only would the variance be infinite, but the mean would be infinite. Okay, it's a very fat-tailed distribution that these popularities tend to show, and that's quite typical of things that are seen like this in social spreading. Okay, I'm going to talk about memes. A meme here is basically a unit of information, a piece of information that gets spread through a network, through a social network, for instance. I'm going to talk about hashtags in a little while. People talk about URLs. You can be more careful and dig into the details of what a meme is and follow it. But the essential idea is, let's think about the movement of information through social networks. And lots of people are doing very, very interesting work. I want to talk to Esteban about this in particular because they've got a very nice model back in 2011. They were looking at emails actually, back in those days. But more recently it's about Facebook and Twitter and information spreading on those. But what I think, what I want to talk to you about is a null model for looking at the network effects and the human memory timescales, which I think are the two crucially important things that are important in these kinds of spreading. What is a null model? I think you're familiar probably with the idea of a null model. It's a model which is not claiming to exactly model or exactly give you everything in the actual real world, but it's trying to be, first of all, simple enough to be analytically tractable and realistic enough to capture certain of the features. Okay, and I suppose the good part of a null model is that it doesn't capture everything, so it allows you to pick out certain things and say, look, there's aspects of my null model that are clearly not being met here, and I need to include those in a more complicated model to capture more complicated features. I'll show you some examples of that later on. So, we're going to think about the effect of a network structure. Again, this is a static network, but it's a directed network, so I'm going to have arrows here, and my arrows, in contrast to some of the descriptions of Twitter, the arrows point in the direction the information spreads. So A sends a tweet, it's received by B and by C. Okay, so the followers, again, the arrows point to the direction the information goes in, just to avoid confusion. And I want to talk about memory. So I want to think of people scrolling back through their Twitter feeds, and if they're going to retweet something, to think about it being from some time in the past with typically a decaying probability. So if I look at my Twitter feed, it's quite likely if I'm going to retweet something that I received or so in the last few minutes or hour, and less likely that it's something that I received a week ago. Okay. All right, so let me give you the essence of the model in a cartoon, and we'll talk about some of the details then. So this is time running this way. Here are 3 of my typical users, A, B, and C on Twitter. They're connected to each other, so let me draw them as a network like this. And time is running this way. These are somehow a cartoon of their Twitter streams, or what they're thinking about in maybe a more general sense than a Twitter one. Here's user A. At this time, user A becomes active. So when a user becomes active in this model, there are only 2 things they can do. They can either retweet something, or do something else with probability mu. So the retweet probability is 1 minus mu. This guy's going to retweet, so I put a retweet here in his timeline. And when he retweets, he looks back in time, so he picks a time from his memory distribution, goes back that distance with some probability given by phi. So in this case it picks here, and he looks at what was in his stream at that time, so it's this red meme. And then he retweets that to his followers. So everyone who follows A sees this red meme appear in their timeline at that stage. Okay. Now I'm only going to color it in these guys' timelines if they find it interesting. In this case they both do. So in general, there's lots of tweets I get that I would not retweet. So that's somehow captured to this interestingness parameter lambda. That's the probability that I'll find it interesting and actually consider it for further retweeting myself in the future. At a later time t2, user C becomes active, and user C does the same kind of thing. He says, okay, I'm going to retweet. So he looks back in his timeline, and he, in this case, looks back not quite so far. He finds the red meme here, and he sends that on to his followers, who are not drawn here in the schematic. Okay, so you can see that that spreads the red meme, whatever it is, whether it's an actual tweet or a hashtag or a URL or something else. These are sort of generic cartoons of information spreading. Okay, so I told you there were two things that could happen. The first one is the retweeting event. The second one is innovation. So that's what happens here at time t3. I'm back to user A again. He's become active again. At time t3, instead of retweeting, he's just come up with a new idea, something he wants to tweet himself. So it's an innovation. So we call that a blue meme. It hasn't appeared before. So that goes in there, and that's his innovation. So the blue appears in his stream, and then it is retweeted at. So everyone again finds that interesting, puts the blue into their stream. Okay, and that's it. There's nothing else in this model other than everything I've just told you. Okay, there is no pictures of cats. There are no any other factors that might make some memes more interesting than other memes. Okay, they're not actually genuinely colored. They're just distinct objects in a class of sets. So again, to recap, there's network structure. There's a structured network. One thing I should have mentioned to you here: B, you can see, follows lots of people, more than A or C in this cartoon, and that means that he receives more stuff per unit time. Okay, so you can see his timeline is busier here than people, and that's an important factor in the model. I'll come back to that. But anyway, there's the network structure, there's the memory time distribution, this probability that I look back a certain time t, that's the phi distribution. There's the innovation probability, basically the chances that when I become active that I'll either innovate or retweet, so that's a single number mu. And finally, there's this parameter lambda, the interestingness parameter. Okay, so four essential things: structure, memory, innovation, and interestingness parameter. So it's simple in that sense, but it's rich enough that it has a lot of interesting dynamics. It also has a lot of very, very nice mathematics in it, which is very complicated, and I won't even try to explain to you, but it's a branching process structure for perhaps fairly obvious reasons. The red meme is here. When it's retweeted, it sort of grows possible children, or children trees, if you think of it as a tree. Each of those may in turn branch more trees in the future, or may not, depending on how things are found interesting. So you can write down a branching process model which takes in the network structure. This is the probability that a node follows j people and is followed by k people, so that's a joint distribution there. There's this innovation probability mu. I didn't talk about activity rates, but we can include the fact that some people are more active on Twitter than other people, typically depending on how many followers they have or how many people they follow. This is the memory time distribution, the phi that appears here in this picture, and finally the lambda thing here. So, and what you get are expressions for complicated integral differential equations for things like this generating function g. So what I'm really interested in is the probability q that a meme is tweeted n times. And if you remember the picture that I showed you at the start from the URL data, I want to know what's the probability something is retweeted 0 times, once, twice, 3 times, and so on. That's qn. It depends on how old the meme is in the system, the age. Okay, so I'll show you pictures where I'll talk about, this is where the meme first appeared, and at age 1, so 1 unit time later, at age 10, at age 100, it's got various levels of popularity. And these things are called generating functions. They're the mathematical objects we use to describe it. If you just simulate it and look at typical or example memes, this is some examples of things that you might see happen. You might see, for instance, that the meme is tweeted once, and then it takes off, and it starts to grow quite. So this is the total number of times it's been tweeted, popularity n. So it has to either go up or stabilize. It can't go down because it's the number of times it's been retweeted in total. And this one is just roughly going up at a steady rate. This one starts off similarly going up at a steady rate, and then around about here something happens and it goes up at a faster steady rate. This one goes up at a steady rate, then saturates, and this one has just died. Basically, it's not being retweeted anymore. So this one is an old meme, if you like, in the system, and it's died. And this one started off growing, then it sort of saturated, but then it got a reboost and started to grow again, and then it saturated, and then it started to grow again, and then it saturated again. It is interesting, I think, that you can get all these varieties of behavior from that very simple model. It is tempting for us, if we were to find this kind of behavior for a picture of a cat, to deduce that something important happened here in terms of the history of cats, or something happened in this case here and here, but I guarantee you that nothing extra was fed into the model. It was simply what I showed you. It is the random fluctuations, or if you like, the competition between the memes in that simple setup that has driven this kind of variety of behavior. In fact, the analysis shows us that this is a question, yeah?
Is there any influence of the network structure?
Yes, there is. Yes, there is. So, I mean, what probably has happened here is that a meme was tweeted by someone who has a lot of followers. But in this particular example that I used here, the network structure is not particularly fat-tailed. I will show you one later on where the number of followers is. So I think this is on their training graph, in fact. So this was tweeted by someone who happened to have more than the average number of followers, but not orders of magnitude more, just a few more in this case, and that happened to be enough to set it up like that. So there is network structure effects there, yeah, for sure. But more importantly is that the dynamics is poised near a critical point. So this is a phenomenon that we've called competition-induced criticality. It's a lot like self-organized criticality for those who remember that or are familiar with it, SOC, but subtly different in the sense that it's critical for those of you familiar with branching processes in the sense that the branching process is critical, and I'll explain that to you very briefly in a second. And it only happens when the innovation rate is quite small. So when most of the time people are retweeting, the essential idea is that people are retweeting stuff a lot. So a lot of stuff is appearing into people's streams all the time, and the probability of something actually surviving and getting sent out by someone and spreading itself like that is exactly like a critical branching process. So the probability that one thing comes in is exactly roughly the probability that one thing will come out of the other side. It is a lot like, but not identical to preferential attachment, for those of you who know the Yule-Simon model of network growth. In particular, the age, the memes who are in the system at the start of the simulation, and the memes who are innovated and appear in the system halfway through the simulation, they have equal chances of becoming popular. It doesn't have this early mover advantage that preferential attachment models typically do. Let's just talk briefly about the criticality. The expected number of children of a meme. So you remember that red meme started off in the stream of user A and it got retweeted twice. Okay. So if we call the number of times it's been retweeted the number of children that it has, well, that depends on when it's retweeted from a JK class node. They have K followers, each of them finds it interesting with probability lambda, so that's the probability to be accepted into their streams. This is the probability that the node becomes active and does the retweeting instead of innovating, which it could have done. And this is the probability that it survives long enough in the stream to be retweeted. Okay, so it's kind of a lifetime length. This is the probability it gets retweeted, and this is the number of streams it goes into when it is retweeted successfully. And if you average that over all the JK classes and do some cancellation, it turns out that the average branching number is 1. Or at least it's 1 when mu goes to 0. So in the case of low innovation, you get a critical branching process. Again, if you're familiar with, this is a bit like being poised at the epidemic threshold. It's at the situation where the fluctuations are very large, where the typical trajectory does not grow, but there's a variety of possible sizes. So if you look at the distribution of outbreak sizes, or in this case the distribution of popularities of individual memes, and you compare them at different ages, then in the system, this is basically a distribution that shows you how popular things can be. So it's a bit like the empirical work I showed you at the start. Most things appear only once in the data set, but some of them, a few of them, are retweeted very, very many times, and those typically are scaling a bit like power laws, at least with very flat tail distributions. The black here is from numerical simulations in the model. Again, the colors are from the analytical treatment that I'll give you some clues on in a minute. This one, come back to your question about network structure, this one is on a network where it has a structure, a fat-tailed structure network, a power law distribution in the network. This one is for an Erdős-Renyi network where the degree distribution is Poisson. So both those cases, and even in this case, the Poisson case, you end up with a popularity distribution that's very, very fat-tailed. It has an exponent of about 1.5. These are the exponents you get if you watch the memes and you wait long enough. You either get a 3/2 distribution with an exponential cutoff, or you get a parallel distribution with an exponent that's between 1.5 and 2. Again, somewhat like what's seen in empirical work. Okay, I'll tell you one more thing. This is that instead of looking at the distribution, if we only looked at the meme popularity, okay, it's an easier thing to think about. What if I look at all the memes who are of age 5, all the memes who are of age 20, all the memes who are of age 100? What's the average popularity? What's the expected number of people that might be reached by a meme after it's been in the system for a certain length of time? So again, it turns out that we can get an analytical expressions in terms of a Laplace transform, but that's as much as you can get in closed form. And depending on the different types of memory that you might use in this system, and depending on what kind your network is, the average grows. So the average popularity grows over time. It tends to grow roughly linearly. okay, for a while. So you can see there's a roughly linear growth with age. This is on longer time scales, it saturates. Okay, we can understand that. And depending on what kind of memory time distribution you have, so the big difference here between the exponential memory distribution, that's just an exponential distribution, and this gamma distribution that we're using here, the gamma distribution has a whole lot of probability mass here at very early times. So the gamma distribution says you're very likely to tweet stuff from the very recent past and less likely to tweet it from the far distant past. How that affects the average popularity is that you get this kick at the start, so that instead of growing linearly as the exponential, you see the red ones do here, the blue ones you can see rise up super linearly at the start and then hit their linear growth before they all saturate at the same level. And we can do asymptotics for that, so that's the linear growth with age. We know how fast that is depending on the average degree, the interestingness parameter, and the average memory time, the mean memory time t. That's the long-term mean, which depends on 1 over the innovation rate. So we can understand quite a bit from the asymptotics of the model. I'll skip this. And just hope that tells you enough to understand that this is a model that is analytically tractable. I'll finish this section then by just showing you that the other nice thing with this model is that it can be fitted, because we have analytical results, we can fit it quite easily to types of empirical data. So this is from my collaborator Javier Moreno and his group in Zaragoza. They tracked hashtags on a 15M Twitter dataset, so 15M protest movement in Spain from 2011. They tracked several 100,000 hashtags that were used in that, and again did what I said. So a long data set is a year-long data set. Individual hashtags when they first appear in the data set, and then for each hashtag, how many times is it used before the end of that data set. Okay. And in fact, what we're plotting here is for each hashtag we look at when it started, and then we say, okay, after 10 days, after 50 days, after 100 days, how many times has it been retweeted in total in that system. Okay. So that's what these distributions are. This is after 10 days, this is after 50 days, and so on. So you can see that the distributions continue to change even after a very long time, which is the first interesting thing. And they have a very fat-tailed structure to them. As you can see there, they're on a log-log scale. That's the actual distribution. If I just go back and again think about the average popularity. So from the pink curve here, the 10-day curve, that's a distribution. But if I just take the average of that distribution, I pick up a number here and I plot it at 8 over 10. Again, do the same thing at 50 days, 100 days. So I'm just saying the expected popularity of something that's been in the hashtag that's been in the system this long, what is that? Okay, so you can see the qualitative feature, you get this roughly linear growth. You can see that it's growing quite fast at the start. So we said, okay, let's take what we know about Twitter, the Twitter network, so the network structure, we'll feed that in empirically. So we went to Twitter and looked at the probability that nodes duplicate. Okay, very easy to query Twitter and say how many followers does a randomly chosen node have. Do that for very many followers, so you get an empirical distribution. And it turns out, at least for a large range of scales, to be roughly like a k to the minus gamma, with a gamma of 2.13 in that particular case. Mean degree, by the way, happens to be about 700, so 700 followers was the average in that distribution, but it's very fat-tailed. So we can feed that directly into our analytical result. So that's one of the ingredients of the model, is the network structure. The other ingredient, if you remember, were the two parameters, the mu and the lambda, and the memory time distribution. We don't know anything about that. There are ways of checking how fast stuff has been retweeted, but nothing that really matches the way that we're using the memory time distribution here. So what we did was we said, okay, let's parameterize the memory time. Let's just think of typical distributions it might be. And I showed you from the numerical simulations that the gamma distribution, a distribution where there was a lot of probability mass at recent times, so it's quite likely that I'd retweet something from the very recent past, that was giving us a kick here at the start that didn't just mean it just grew linearly like that, it grows fast first and then grows roughly linearly. So the gamma distribution was one we used, and then we fitted these parameters, k and theta, quite easily to get the theoretical curve that does reasonably well against the empirical values. And then once we had that, we could go back to the full distributions and ask what the model says about these full distributions. Again, we get asymptotic results for the large end popularity compared to what the data does. One aspect of the data that's interesting is that if you take those distributions and you take each of them and you divide them by their average expected popularity, they almost collapse. And that turns out to be what happens for the model as well. And that just gives it a nice way of putting those together. So if I compare the collapsed empirical data and the collapsed model results, you can see the fit is not bad. It's not great. There's still a prefactor here that's off by a factor of 1.5 or 2, but the general shape of the distributions is good, the exponent is good, and the fit to the mean, of course, is good because we use that. Okay, so the model is simple enough and it can be fitted to data, and that's, I think, interesting. Let me just skip this and show you one aspect where the model doesn't work well in this case. Okay, so I've shown you already the fit to the mean, and I've shown you that the model distributions look pretty good compared with the empirical distributions. We've offset them here by a factor of 10. Here's the scale of ones I showed you earlier. However, it does not do well here. So this Q1 I skipped earlier, but it is the probability that a meme is tweeted precisely once. Okay, so it's the orphan children, the orphan tweets, the tweets that I send all the time that are tweeted exactly once by me, and they're not retweeted by any of my followers. Okay, you're familiar with those? So in the empirical data, about 65% of all tweets were never retweeted. Okay, so Q1 is that the popularity is 1. That's it. They appeared once in the data set. And that's true for, in this case, about 65% of them. However, our model, with all the parameters that did well everywhere else, did quite poorly there. It was saying that, well, that should be only about 25%. So that stuff would get retweeted more than it does in practice. And that's, it's a very simple model. There are aspects to reality that are obviously not captured here, but it does then beg the question, what is missing from the model that we could change? So one thing that we had done here was we'd assumed that everyone tweets at the same rate. So that gave us an impetus to go look at the probability that the activity rates that people have depending on how many followers they have. So for instance, this data set, again, an empirical one where you ask the probability of people retweeting depending on how many followers they have tends to grow linearly like this and then roughly linearly like this. So we put a function like that into our model. I told you we could handle activity rates as well. So we put in one that went up linearly and then linearly again and then saturated for the very high degree users. And when we did that, this same plot that I showed you earlier does much better, okay? And everything else is unaffected essentially. So again, it's a null model, but one of the things the null model is showing us is that heterogeneous activity rates make a difference to some, but not all of the characteristics that are somewhat characteristic of mean popularity on social networks. Okay, so that was the idea here that we had analytically tractable results and empirical data fitting. And I guess to conclude this second part, just this idea of the competition-induced criticality I think is important. It potentially can drive lots of different situations in social networks where there's basically people are overloaded with information. So there's an information overload, there's a lot of information coming in. You have to select from that set of possible information to select what you send forward. And if the retweeting kind of mechanism is the dominant one and innovation is rather low, then I think quite generally you'll see this type of behavior in a social network system. You particularly get these parallel popularity distributions of exponents between 1.5 and 2. The nice thing with this model is it's simple enough to be analytically tractable. It's realistic enough to capture at least some of the features in empirical data, and I think for those who are fans of pictures of cats and there's a lot of interest in the content of the tweets. What is it about the tweet that makes it go viral? Well, this model has no content. It has no features at all. But if you want to have a model that looks closely at content, I think it is important to compare it with null models. To me, the most interesting part of this is that in a very simple model where really it's only random fluctuations that drive the behavior, you can still get a lot of the characteristics of real-world data without having to put in extraneous features. So in that sense, I think it's a null model that hopefully can be helpful to others. Okay, so I don't know if I'm ahead of time or what, but I guess I'll leave some time for questions. Let me just remind you what we spoke about. In the first part, I was concentrating on differential equation models. We were looking at dynamics, which took up a sizable fraction of the network, so the number of nodes infected scaled with the size of the network in the large network limit, and trying to come up with approximation schemes that were like mean field but better in some senses. And in the second part, I went back to the subcritical phase. That's in the branching process sense. The outbreak sizes don't scale with the network sizes. The n goes to infinity, or in fact, some of our cases are close to criticality. And there we were really looking at the distribution of outbreak sizes. And in contrast to here, where everything was Markovian, here at least we're starting to think about the problem of non-Markovian memory and these memory time distributions. Okay. Again, thanks to my collaborators in the group in UL and the international collaborators. These are some references, and I'd be very happy to take your questions. Thanks.
So I know it's ignoring what the content is, but suppose before I look at my feed, 6 people have retweeted a particular meme. Now what Twitter will do is it will, just move that meme to the front of my feed, but will say, hey, 6 people have already retweeted this.
There's certainly none of that included in the model. So this, if you like, is a model closer to Twitter from several years ago than the current updates on Twitter. We have been thinking a little bit about not that particular point, but the advertisements on Twitter, so the stuff that you see in your feed that is not from people that you follow. The model says that reduces the criticality of the system. It pushes the system slightly away from the critical point. I don't know if Twitter cares about that. I don't know if that somehow does affect the likelihood that things will go viral on Twitter by some extent. But no, it certainly doesn't account for I suppose the hard work that's done behind the scenes by the algorithms, certainly on Facebook, for instance, on newsfeed, but also more and more on Twitter as well. That stuff gets moved up. What is also not in this model is the idea that you even know how many times something has been retweeted. Okay, that's a relatively modern feature as well. And I guess that can affect, that's more like a preferential attachment model where you see something that's been retweeted by a lot of people and that makes you more likely to tweet it. Not because it's interesting to you necessarily, but just because it's been retweeted in the past by a lot of people. So that would be a hybrid that would need to be grafted on here, I think. But I guess we sort of deliberately avoided making things more complicated than we thought we needed to after we put in the kind of straightforward features.
More questions?
These examples which you showed for us, the age, actually what was this? It was in months or in years?
So in the empirical ones, these are in days. The model itself has a time scale, which is just a time scale that you set. So it's basically, I said there's a rate at which users tweet, so that we normalize the time scale by the rate at which users tweet. So we have to fit to empirical data. But if your question was about the actual hashtags that spread in the Spanish 59 protest movement, these are actually in days. Yeah. And I think it's interesting and kind of non-trivial that even 150 or 200 days after the hashtag first appeared in the thing, that its distribution is still changing. Yeah. So, yeah.
How many similarity classes we have? So how many types of people we have on Twitter? How important are trends, for instance?
Good question. And outside my regime of knowledge, to be honest, I think there are certainly people in the computer science community who look at classification of users by behavior. I think that's an interesting and potentially very important in the digital marketing world question. In terms of the model, all that we have for users are the number of people they follow and the number of people who follow them, so their JK class, if you like. And in fact, in a lot of the results I've shown you, we've assumed that people just connect to people at random, so we're really just interested in the number of followers that people have, along with, and that can influence their activity rate, how fast they tweet. But that's really all we have. So we've just put that in as the input in terms of the model. In practice, I think that's a good empirical question. I don't know the answer to that.
According to the first part of your talk, I have a question about models which are not linear. For example, Kubolter, I don't know.
Yeah.
And how you think it will be the same situation that master approach will be the best one, or in this case, class of model?
So QVoter, you mean?
Yeah, generally no linearity.
Non-linear dependence on the number of people who are in a session. Sorry.
If the master approximation of master equation will be the best one?
Oh, the best one. I showed you an example, I probably won't be able to find it now, but I showed you an example for the majority vote model, the QVoter model, where the master equation approach is very accurate, but neither the pair approximation or the mean field were accurate in that case. Why is that? Technically, that's a non-equilibrium, in a statistical mechanics sense, a non-equilibrium system, right? I don't know of any general way of approximating that accurately. So I guess the answer is yes. As far as I know, that's and then the follow-on question is that always guaranteed to work? So the master equation approach, I didn't show it to you here, but if you look at adaptive networks, so if the network changes in response, Even there, the AME is not as it's more accurate than the other two systems, but it's not always guaranteed to be accurate there either. So some of these systems can get very, very complicated close to critical points.
That even is criminal data.
Even then, yeah, sometimes.
Okay. So I believe we'll have to thank